the same day as the press conference, pretty much at the same time, there was a paper released describing everything about this detection. That paper had 1,004 authors, which indicates a small fraction of the effort that has gone into this detection over decades. And two people at Southampton were on that author list. One of them is Dr. Ian Jones, who is a member of our gravity group at the University of Southampton and a member of the LIGO-Virgo scientific collaboration. And he will be talking about gravitational waves.
Thank you, Ian. So it really is a pleasure to come here today and tell you about a story where we're not promising something in the future, where we've actually got something in our hand now, something exciting to tell you about. So, the press conference that Ian just spoke about took place on February the 12th of this year, and it was to announce the detection of gravitational waves. The thing that made all this happen was the detection of this couple of little squiggles that you can see on this plot here. It might not look an awful lot at the moment, but it really is. It was a very big thing when it was seen. It was greeted as big news by the media. The BBC, because we weren't sure how much attention the media were going to pay to this story, the BBC ran this as their main story on both the 6 o'clock and the 10 o'clock news that day. Various newspapers picked up on it and ran with it. The Independent put a big old picture of a simulation of a pair of black holes which produced these gravitational waves on their front page. The Daily Telegraph put sort of an artist's impression of what a certain sort of black hole might look like, not quite so closely connected with what was actually seen, but it was a very nice picture to put on the front page. They couldn't give quite as much of the front page as normal to the EU, and even less to Downton Abbey. So a real cost for them, but they did it. And this was sent to me by a colleague. Apparently, this a reference to this story even made it onto the front page of the big issue. The story itself was about something slightly different, but there was a reference there. So that was nice to see. And also, by looking around on the internet, I found that various musicians had made use of this event. That signal that I showed you, I'll have a lot more to say about it in a moment, but it turns out that the sort of frequency content is the sort of frequencies that our ears are sensitive to. So if you translate it into an audio signal, you hear a little chirp, and so musicians were quite quick to take advantage of this. Those little chirps are the actual signal.
Back home, I wanna hear you all. Just back home, wanna hear you all. Just back home, I wanna hear you all.
Okay, there won't be any more of that. But there's still the chirping sounds that were incorporated into the first section of that. That's what you get if you take that gravitational wave signal and you translate it into the audio. So, what am I trying to do in this talk? Well, I want to tell you what a gravitational wave is. I want to explain why the detection of these gravitational waves by the so-called LIGO experiment really was a big deal. And to do that, I need to go back some way. The announcement was made in February of this year. The actual signal was detected in September. The experiment began, in a sense, in the 1990s. Other experiments began in the 1960s. It goes back a long way. And if you really push it all the way back, on the back, it goes to Einstein himself. Okay, but this is what an Einstein thing, and it was Einstein's theory of general relativity that led to the important ideas that I'm going to tell you about now. So one of the ideas in his theory is that this theory of general relativity is basically his theory of gravity, our modern theory of gravity, and it describes gravity not as a force but a curvature in space-time. That's a rather sort of profound and deep idea. We don't need to go into it too much. The more important thing in terms of what I'm going to talk about now is that Einstein's theory of general relativity, just like his theory of special relativity before it, incorporates a universal speed limit, and that speed limit is the velocity of light. Einstein said that nothing could travel faster than the speed of light, and in a sense that's got some quite profound implications for other aspects of physics. And in particular, it's intimately connected with the idea and existence of black holes. So just 1 year later, so we've gone from 1915 to 1916, Carl Schwarzschild found a solution to the very complicated equations that Einstein had come up with. It wasn't called a black hole at the time, that name came later, but he had found a black hole solution. Black holes have got a peculiar property that basically if something falls in and gets too close to them, it never gets out again. And in a sense, that can be understood in terms of this universal speed limit. If nothing can go faster than light, but if the gravitational field of that black hole is so strong that light can't escape, then nothing can escape. So that's one of the important ideas that goes into this. Now we already have quite good evidence that black holes exist. This evidence has been around for years now. And in fact, we think that black holes in nature come in sort of two varieties. The so-called stellar mass black holes. This, of course, is an artist's impression, but it's a particular black hole that's believed to exist is Cygnus X1. Black holes are black. Why is it that we think we know that they exist? Well, black holes are often found, all the black holes we know about, they're in so-called binary systems. The idea is you've got a tiny little black hole in there, and you've got a main sequence star, a big star, in orbit around it, and that larger companion star is losing some of its matter, it's flowing onto the black hole, it's forming an accretion disk, and what's happening to that gas is it's being compressed, and just like if you pump air in a bicycle pump, you know it gets hot. Well, it's the same phenomenon going on here. Compressing that gas makes it heat up and it glows in the X-rays, and that's what gives rise to that sort of image that an astronomer can actually look at and see. So we already have some good indications of stellar mass black holes. We also have indications of much more massive black holes. And in fact, it's believed that most, or possibly all galaxies, have got a very heavy black hole. Say millions of times more massive than our sun, possibly hundreds of million times more massive than our sun, looking at their center. And one of the pieces of evidence for that comes from looking at the center of our own galaxy, the Milky Way. And what I'm going to show is actually an animation that, based on real data. That little star at the center is going to denote the position where this very massive black hole, mass 4 million times than in our sun, is believed to exist. And these other glowing things, they're stars, and once I hit play, we're going to see those stars move around. And the key point is that they're going to move around in such a way that it's suggestive that there is a very heavy mass here. So for instance, let me reset that. What we'll do is we'll focus our attention one of these stars, and the time in years is going to tick away at the top right. So if you look at that purple trace, right, so using the laser pointer as resetting the movement, press it again, it doesn't go again. So you're going to have to just draw your attention to the mouse. If you look at that, right, so that yellow curve star is just spun around a massive black hole. Look at this purple curve that's being traced out now. Again, the star is going close to the central black hole, and then it's being rapidly turned around in its orbit. So that's one of the pieces of evidence that there's a supermassive, very heavy black hole in the center of our galaxy, and we believe many others. Now, these sorts of pieces of evidence that black holes exist are good, but they're not very, very direct. And what we're really saying is that there's some very strong source of gravity for both the stellar mass case and here. And we can't think of anything other than a black hole that could possibly have that amount of mass and that small volume. But Einstein had a lot to say about the detailed properties of black holes, not just that they've got very strong gravitational fields. And it would be nice to be a bit more quantitative than this and actually learn in a bit more detail about the properties of these objects to see if they really match up with Einstein's predictions of what black holes are. And that's what we're going to try and do when it comes to gravitational wave detection. So what about gravitational waves? Well, this was all happening fast because again in 1916, so just 1 year after he published his theory of relativity, Einstein realized that this speed limit that I spoke of, nothing can go faster than light, that had implications changes in the gravitational field, if I wave my arms around, I produce a time-varying gravitational field. But what happens? How does that change propagate out? Well, Einstein looked in detail at his equations, and he looked at small little changes in the gravitational field, and he realized that these small disturbances would propagate at the speed of light. And these are gravitational waves. So gravitational waves you can think of as ripples in the gravitational field, ripples in space-time. They're things that travel at the speed of light and represent the changes in gravity as objects move around in some way. Now, so I'm not an expert on the history of this. I'm just going to devote one slide to this. I don't want to oversimplify the story because it turned out that people, Einstein himself, weren't actually completely convinced that gravitational waves were a real thing. And the reason for that is, okay, so he looked at the equations and he saw something propagating at the speed of light. But does that, just because you see it in your equations, does it mean that it's real? I mean, to be sure that something is real, you've got to understand what effect it has, say, on a measuring device, on a ruler, on a clock, on a laser, on something, right? You need to be sure it's not just a trick of the maths and it actually affects something. And so this quote's taken a bit out of context, but Sir Arthur Eddington, that we heard a lot about in the last talk, he did once say that gravitational waves or semester can travel at the speed of thought. I don't think he was an out-and-out skeptic, but it's a very nice little phrase. That, so what do we think about gravitational waves? Of course we think they're real, that's the, and now we've detected them, that's the whole point of this. They are small ripples in the gravitational wave, in the gravitational field. They do travel at the speed of light, but crucially what people manage to convince themselves of by thinking about this very carefully is they carry energy, they carry momentum, can't get much more real than that, and one way of thinking about the effect of gravitational waves is that they exert small forces on objects. There's gravitational waves passing through us all the time, even right now, okay? And you can't feel them because they're very weak. But what they're doing is they're exerting very, very small forces. Oscillatory just means that they're, they're sort of pulling you in and out all the time. Very small forces on you all the time due to these gravitational waves. And people often illustrate that by saying that if you had a ring of little freely floating particles that's initially laid out in a circle, and a gravitational wave would have come along, say, in this direction here, propagating into the screen, then that initial perfect circle will be distorted into an ellipse, first with its axis one way, back to a circle, back to an ellipse stretched the other way. Basically, this is stretching and compressing force that's due to this passing gravitational wave. So they're real. They do affect things. What produces gravitational waves? Well, the answer to that is pretty much any motion of mass. So as I said, when I move my arms around, that will produce gravitational waves, or every waves. The beating of my heart, that produces gravitational waves, not just my heart, everyone's heart. Almost any sort of motion of mass produces gravitational waves. But the strongest gravitational waves are those produced not here on Earth, or indeed anywhere nearby. The strongest gravitational waves, and the ones that we might hope to detect, will be produced by violent astronomical events. Why? Because you need big masses, you need big accelerations, you need violent going things on to produce significant changes in the gravitational field. That's what produces the strongest gravitational waves. And that's exciting because it means that we might learn about some of the most violent and some of the most poorly understood things in nature from looking at gravitational waves. So for instance, and the thing that's going to be relevant to the detection, if two stars collide, and typically they won't do it head on, they'll do it by swirling into one another, say a pair of black holes, that will produce gravitational wave emission, so-called binary inspiral, or the collision of compact stars. When main sequence, when normal stars reach the end of their life, they can explode, the famous supernova explosions. Those explosions can produce gravitational waves. Rotating neutron stars, so a neutron star is a very, very small dead star. The mass is something like the sun, compacted into a sphere of about the size of a city. Incredibly dense. We'd love to know more about what they're made from. Well, they're so dense such that if they are wobbling in some way, or if they've got some sort of mountain on them, or some sort of wave disturbance on them, that will produce gravitational waves. That's what And then finally, it's inevitable that in the very early universe, there will have been some production of gravitational waves. This is a picture, you've seen it already this morning, of the electromagnetic, the cosmic wave background as viewed in the electromagnetic channel, in the microwave channel. We don't know, we've not detected the gravitational wave background, but there will be one that will tell us about the universe when it was even younger. So this tells us about the universe when it was about 380,000 years old. We'll learn about the universe at a much earlier time, a fraction of a second, if we ever see the gravitational wave background. So basically, the big, interesting things in astrophysics can produce gravitational waves. Now, I said that we had good reasons in terms of understanding the maths to think that gravitational waves are real. We've also, for some years now, had some experimental proof, but indirect proof that gravitational waves exist, and that's what I'm talking about here. I mentioned that if you've got two stars in orbit around one another, they'll produce gravitational waves. Energy will be carried away. Well, that energy, that's got to come from somewhere. You can't make it out of nothing. It comes at the expense of the orbit of these two stars. They'll very gradually spiral in towards one another. And this effect would be negligible in most binary star systems, but there are some star systems built out of pairs of neutron stars, but because they're so dense, the stars can get very close together, and that gravitational wave energy loss can start to become important. And it's precisely that shrinking of an orbit that was measured by some radio pulsar astronomers, in fact, and what they found, this is a famous plot, and the exact quantity here is to do with one of the parameters that used to describe this orbit. The basic point is that these little black dots are data points that depend on how the orbit is shrinking as a function of time, and that black curve that you can see passes neatly through them, that's the general relativity prediction of how that orbit should shrink if it is indeed losing, if it is indeed radiating gravitational waves in accordance with Einstein's theory. It's a good agreement, but it's indirect. We're not detecting the gravitational waves, we're just seeing their effect on an existing star system. And also, these two stars, they're quite some way apart. Typical velocity in that system is about 1,000th of the speed of light. We'd love to learn about systems that are traveling closer to the speed of light to get a stronger, more violent test of Einstein's theory. So that's where gravitational waves come in. They offer us the hope of seeing gravity and work in much stronger, more violent circumstances. So how do you actually go about directly detecting the gravitational wave? Well, I've basically already given you the answer to that. You exploit the fact that gravitational waves tend to make objects shake ever so slightly. So if you're clever enough to build a machine that's so well isolated from all the terrestrial sources of seismic noise that when it starts shaking you can say, ah, that was a gravitational wave, then you've done the job. The problem is gravitational waves are so terribly weak, it's technologically extremely difficult to build such a seismically quiet, such a vibration-free device to do that. But people tried to do it, and early work started in the late 50s and 1960s. This chap here, Joseph Weber, pioneered the so-called bar detectors. They're basically big metal cylinders, and the idea was that if a gravitational wave came along, and if it had a frequency close to the natural resonant frequency of that big bar there, you'd see it start shaking, and you'd have detected gravitational waves. And there's a bit of historical controversy here, because in fact he claimed to have made detections quite early on in his quest. Other people didn't agree. They tried to reproduce his findings and they couldn't. To the day he died, Joseph Weber thought he had detected gravitational waves, but the mainstream science, it was very clear that in fact he hadn't. And one of the difficulties is when you've got this sort of size of apparatus to look at, the effect that you're looking for really is very small indeed. And so the modern way of doing it is to, in a sense, make your machine much, much bigger, far bigger, and instead of having a big metal bar, what you have instead is a mirror here and a mirror here and a laser here. This is an animation, I'll play it in just a moment, and the idea is you're going to fire a laser through this system, and if a gravitational wave comes along, it makes the whole thing shake, it makes this thing move back and forth, it makes this mirror move back and forth, but in different ways, and it will change the relative length between these two arms of your experiment. So let me play this. So you can see a laser's being fired. It's being split into two parts at this so-called. I've done it again. I mustn't press the laser pointer button. It's being split into two at the so-called beam splitter. If a gravitational wave comes along, it makes those end masses shake. But how do you actually detect that? Well, this is laser light. It's light with a very well-defined phase. It's a sort of very pure light. So when it's reflected, we can still trace the wave coming back to the beam splitter. And so we're going to try to, this is our sort of detected readout here. We've got waves impacting on that. Some have travelled up one arm of the device, some along the other. And the way in which they interfere here, it can be either constructive interference if the two peaks are adding up, or destructive, will change the amount of light that we get there. But the exact phasing of these waves as they arrive here depends sensitively on the length of this arm, and it depends on the length of this arm. If you make this arm a bit shorter and that arm a bit longer, you'll change the relative wavelength of the waves arriving there. You'll change the pattern there. So it's as if you've got a big experiment. Well, you have got an experiment whose effective size is the distance of the two sides of this L, the so-called interferometer shape. And that means you don't have to build a metal bar of 1 or 2 meters. You can make your experiment much, much bigger. And it's precisely that idea that is exploited in the LIGO experiment. So this is basically the L shape here. All of the action, the laser, and the readout is going on in the so-called corner station over here, but the distance from here to here is 4 kilometers. And there's a mirror there, there's a mirror there just off screen. The laser's being fired up and down one arm, fired up and down the other, and recombined there. And so the LIGO project itself consists of not just one of these machines, but 2. This one here is the so-called Hanford detector, which is in Washington State, so the top northwestern corner of the USA. There's another very similar, almost identical LIGO experiment down in the bottom southeastern corner in Louisiana of the USA. As always in science, you want to have 2 experiments, because then by comparing the output of each, you can be more certain that you've seen something. So the key point, the arms really are 4 kilometers long. The sorts of gravitational waves that this is sensitive to will correspond to a fractional length change of these arms of 1 part in 10 to the power 21. What do I mean by 10 to the power 21? I mean 1 followed by 21 zeros. So it's a very, very small fractional length change that these experiments are sensitive to. And to put that in perspective, if you multiply that up by the size of the detector, they're sensitive to actual length changes of a few times 10 to the minus 15 meters. And that is what you get if you divide 1 by, or then 1 followed by 15 zeros. So it's very, very small. It's comparable with the size of a proton. So it was an incredible feat of technology, as was discussed before, we pulled this off. The LIGO experiment actually started taking data around about the year 2002. Let me explain this slightly more technical plot. This is a graph of the frequency of gravitational wave that you're looking for versus some number that's basically a measure of the amount of noise, the amount of scruff in your detector. So what you want is at any given frequency, you want these curves to be as small as possible. And this is the state of the detector in about 2002. And then in the so-called first science run S1, the next science run about a year later, we've got the green curve, and they very, very gradually improved the detector to the point where they reached this black curve, the so-called initial design sensitivity. So there was a lot of patient work that went on gradually improving the detectors. Lots and lots of analysis was done on the data that came out of them. No signals were found. So the LIGO collaboration published about 100 so-called upper limit papers. An upper limit paper means that you've got a load of data, but you've not seen what you want in it, but you still try and interpret it in a, to say what you can conclude from it, but you've not yet seen the thing that you were looking for. At that point, as was always part of the plan, the experiment was shut down for a few years, and then it came back very recently in September 2015. Those first experiments were called the initial LIGO experiment. The new experiment is called the advanced LIGO experiment. And Okay, so the things started taking good science data on September the 12th, 2015. This is what happened on September the 14th. Okay, there's a typo there. On September the 14th, so just 2 days into the data taking, a signal arrived. Well, something happened at the LIGO-Hanford detector, something happened at the LIGO-Livingston detector, and remember I said it's important to have 2 detectors to give you more confidence that what you're seeing is real. Well, I also said that gravitational waves propagate at the speed of light. Well, if you take this signal and you delay it by 7 milliseconds so that you could line it up with this signal, which really was the light crossing time between the 2 laboratories, you can see that these 2 signals match up rather well. Now, this detection wasn't made on the basis of just eyeballing it. There were very sophisticated methods used. But the point is you could almost see by eye something in the data. So very sophisticated methods were in place. We could have detected things which by eye you couldn't possibly have seen. To be able to see this thing by eye was absolutely incredible. Nobody thought we'd be able to do that. An automatic alarm sounded in the detector within 3 minutes. A few hours later, people were sending around emails saying, has anybody deliberately put in a fake signal here because something interesting has just happened? Well, nobody had injected any fake signals. We do that sometimes to test it, and it looked real. And so then, 6 months, an extraordinary 6 months later, where this result was attempted to be kept in complete secret, after lots of checks, every single possible check you could think of, including a people commissioned to go away and say, all right, if you were a malicious hacker, could you have hacked into the system and put a fake signal in it? Well, no, certainly not. After all the checks were done, this is what happened. There was a press conference and a paper observation of gravitational waves from a binary black hole merger. You can actually go and look at it yourself if you want. It's freely available from Physical Review Letters. So this was really the culmination of this 100-year story. It was an extraordinary day for those of us that have worked in the field, and I'm sure it's even more extraordinary there's some colleagues that have worked in it for much longer than I have, to be able to finally, after all these efforts, all these upper limits, all these non-detections, be able to say we've detected something. So what had we detected? Well, we really do think we've seen the coalescence to black holes. There's a cartoon schematic of what was going on up here. The idea was black holes started off relatively far apart. They were in a binary, so they're orbiting one another. So just as I said before, they lose energy, they get rather close, they eventually merge. And what happens then when 2 black holes merge? Well, you actually simply get one bigger black hole. You get a bigger black hole, and then that gradually settles down, and eventually you're just left with one single black hole just sitting there, spinning maybe, but not doing a lot else. And the signal, we know how so there's been a lot of work in the past few decades to solve Einstein equations accurately and actually compute what the gravitational wave signal would look like from one of these binary black hole coalescences. And I said we had confidence this was a real signal. Well, the signal that we've seen does agree very well with the prediction from Einstein's theory. This is what the signal looks like if you just look at sort of theoretical best match. It starts off in a low frequency, the frequency gradually increases, its strength gets bigger, the things merge in a violent way, and then the thing settles down. And to hammer home why this is a very different test from relativity and black holes than we had before, what this graph here, so this is taken from the paper, shows is if you look at the green curve, the initial velocity in units of the speed of light of these black holes was about 0.3, and it ramped up to more than half the speed of light. We're not looking at the weak field, slow motion limit. This is powerful stuff. This is 2 black holes just as they're colliding. You can't get a stronger test of general relativity than this, and the waveform did seem to match up. The sky location, you get some location on where on the sky this happened by looking at your gravitational wave data. It's not very accurate by electromagnetic standards. And also, because this was a pair of black holes colliding, we don't really expect there to have been a big burst of light from it, because they're black holes. But nevertheless, some information was sent out to astronomers to say, point your telescopes at this bit of the sky and tell us, did you see anything? Most people said no. One group said maybe. It would be extraordinary and very interesting if they really have seen, I think they might have seen a very big gamma ray bursting coincidence with this gravitational wave signal. It would be extraordinary if they had, because no one really expected a pair of black holes to do anything other than emit gravitational waves. The jury is still out on that. So why was this a big deal? That's the question I said I'd try and answer. Well, I hope in a sense I've made it clear. It's a big deal for fundamental science. It's the first ever direct detection of gravitational waves. We had indirect evidence that they existed, but no direct evidence. It's the first ever, well, arguably the first ever strong field test of general relativity, where you see dynamics typical of a black hole. And also, I would say it's the most direct evidence that black holes exist and have the properties as predicted by general relativity. So these are all very big things in terms of fundamental science. But that's only one half of why this is important. The other half, I'd say, is it's a very big deal for astrophysics. So when I put this statement here, we've opened a new window on the universe in quotation marks. I'm not going to attribute that sort of statement to anyone. We've been running this sort of thing, or we will open a new window in our universe, in our papers, in our grant applications, in our outreach talks, for forever. Okay? And what did we mean by that? Well, the point is that now that we can detect gravitational waves, great, we've tested relativity, and we'll keep testing it, but we can learn about the things that produce those gravitational waves. This was the first ever observation of a binary black hole system. We've seen binaries where one star's a black hole, the other star's something else. First time we've seen a binary black hole system. So astrophysicists are now asking all sorts of detailed follow-up questions. Where is the binary formed and from what? It turns out that, so I didn't read out the masses were 36 times the mass of the Sun and 29 times the mass of the Sun for those two stars. Bigger than anything that's been inferred for other sorts of black holes. That came as a surprise. And if it's the case that that gamma ray burst reported by some electromagnetic observers was real, how on earth did those two black holes produce it? So there's all sorts of astrophysical questions that come up. What comes next? Well, this hopefully really is just the beginning. The detectors I've been talking about are these two LIGO instruments in America. There's a sort of a prototype detector that's also working but less sensitive. But there are two big detectors that are under construction, and Virgo will start taking data quite soon, and Kagra not too long after. There's plans to put another LIGO detector in India. By having a whole network of detectors, you'll measure these gravitational waves more often, more strongly. We'll do much more precise tests. You know, we might tease out all sorts of interesting features, and you'll get better sky localization as well. So when you put a whole network of gravitational wave detectors, you can give more precise instructions to your electromagnetic colleagues and say, look at that little bit of the sky over there, not look at that enormous bit. And of course, we hope to learn about more than just black holes. I mentioned spinning stars as possibly producing gravitational waves, exploding stars, possibly gravitational waves from the early universe. We'd love to learn about all of these different things in the gravitational wave channel. And then finally, whenever you're stepping into the unknown, you never quite know what you're going to find. So maybe there'll be a few surprises.
So we have time for questions if anybody has any questions on gravitational waves.
I just ask, how would you expect to find out more about the Big Bang through gravitational waves?
So I did mention, hopefully, potentially finding an analogue for the cosmic microwave background, which does tell you about the universe and the Big Bang. So in principle, it's possible, and it's something that people are looking for. But the numbers aren't very encouraging. We're probably going to see lots of these binary signals, and I hope that we'll see some supernovae. Maybe we'll see spinning stars. The numbers are at least encouraging, I think, for learning about the very early universe and this so-called gravitational background, but also the uncertainties are very large on those sorts of calculations. So it's certainly worth doing, and people are trying, and so it's possible, but it's classified as a long shot compared with some of the other things we're looking for.
This result has been obtained with the the state-of-the-art system, which has only just begun operating like that. What can you see ahead in terms of further improvements on sensitivity of the observatories?
So they will gradually, so in fact they're not taking data at the moment. This advanced leg of the first science run was deliberately stopped last month, I think. The detector's been shut down and it will be worked on for some months, then later this year it will come back with a somewhat better sensitivity. It will then take a slightly longer loaded data, will then shut down again for more work. It always sort of works in these phases. So it's going to gradually ramp up to what's called the design sensitivity. It's somewhere around the year 2020, somewhere around there. So there's going to be sort of incremental improvements all the way. And an important point in that regard is if you make your detector, say, twice as sensitive, it means that you can see a given source twice as far away, but that corresponds to 2 cubed, that's 8 times the volume. So it's hopeful that there are no guarantees in this, but you start surveying a much larger portion of the universe with each incremental step in the detector performance, and hopefully see more signals.
So how much will that enhancement be by 2020 compared with what we have now?
It's a factor of about 3 or 4 or something like that, I think. I don't have the exact number in my head, but it's something like that.
Nice. What's the delay in announcing the result and the double checking very much informed by what happened a year, 18 months before with the kind of the announcement that they'd been detected previously and that proved not to be the case?
So I think you're referring to the BISAC results where by looking at the electromagnetic cosmic microwave background, they thought they saw the imprint of gravitational waves and made a detection which later turned out to be insecure. So I'm actually saying no, that delay probably didn't have much to do with that because this is gravitational wave detection is a field that almost from the outset of the LEGO experiment has been paranoid about making false claims, perhaps in part because of what happened in the 1960s with the Joe Webber. I think there's been a culture for years, possibly decades, of being completely, maybe paranoid is too strong, but being very, very cautious about making any claims. And that 6 months felt like a mad rush, to be honest. It was probably the last thing that could have been done, given the amount of checking that was deemed necessary. That question up the front.
You talk about gravitational waves from the supernova. In that case, if the centre of mass and the centre of energy doesn't, is the same, how does the gravitational wave get produced?
So the actual gravitational waves are produced by the matter becoming asymmetrically distributed in some way, but it doesn't require an actual motion of the centre of mass. It's a slightly more complicated redistribution that's consistent with the centre of mass staying where it is, but the mass nevertheless forming some sort of complicated pattern. So for instance, if in the supernova explosion, as the core of the star collapsed, it formed a sort of a bar shape, that would be an efficient gravitational wave emitter. It's getting that sort of asymmetry that's the key.
You mentioned the US and what's going on in Europe. Is there anything else going on? I'm thinking of Russia.
So in terms of the network of gravitational wave detectors, I mentioned the Japanese one, and then the possibility of putting the plan to put one of the LIGO ones in India. I don't think there's any particular Russian plans or Chinese plans. I think that I know of. No. Front again.
In terms of the frequency of measurement, are there limit bands of frequency where these detectors detect?
Yes, there are basically below about 10 hertz. The background seismic noise becomes very, very strong, and it's difficult to do anything useful. And above about 10 kilohertz, you're limited not by seismic noise, but by noise sources to do with the experiment itself and the laser in the experiment. So there's a sort of a band between about 10 hertz and a few kilohertz, with a sweet spot somewhere around a few hundred hertz, where these experiments work best.
And were you looking at other things that are emitting at those frequencies that you could sort them? But what would typically be the other things that you would be
So
filtering out in that range?
do you mean the other sorts of gravitational wave sources?
Or it's like you talked about, seismic, I guess you said, at below 10, and then are there other things even within the 10 hertz, the 10 kilohertz?
Yes.
You're having to, the mechanical, lots of mechanical.
There's a whole host of sources of noise in these detectors. And I mean, seismic noise sort of groups together lots of things, but quite apart from, one of the plots I showed what's called a noise spectrum, so how much noise you've got as a function of frequency. And one of the things on that plot are lots of vertical lines, and some of those correspond to really prosaic things like the hum from the mains frequency. All right? And others are like the natural frequencies of vibration of the pendula in the experiment. And there'll be others that have got, there's a whole sort of catalogue online somewhere where all these different spikes are. So it's mechanically an extremely complicated device with many different sources of noise. But seismic sort of covers a whole load. There's so-called thermal noise. We've not tried cooling the detectors, but in the future that might happen. And there's also noise to do with the fact that you're using laser in the system as well.
But it's 10 hertz to 10 kilohertz.
Roughly, yes.
Does the fact that two slightly unusual black holes being so close together challenge any other aspects of astronomy? I mean, is that a big surprise? Or?
So I think it wasn't a big surprise, it was a modest surprise to see that system. And there are two parts to it. So people try to make predictions as to how often LIGO should see these sorts of events, which in turn means making predictions as to how often black holes in nature actually coalesce. And the error bars on that were very big. There were some estimates, very few, but some people thought there was a possibility that that number was 0, didn't see any. So those models are being excluded, but there was plenty of room in other models for seeing them at a rate. We've only seen one so far, so that you can't say much about rates, but it was within the bands of expectation that they could see one. The masses, the two component masses, 36 and 29 solar masses, they were a bit bigger than people had expected because the inferred masses for these accreting galactic black holes that people think they can estimate masses for are typically lower, less than 25. And the fact that these are somewhat more massive than that, these gravitational wave source black holes, people think that says something about how they were formed and where they were formed and the chemistry of the region in which they were formed. So people are starting to write sort of follow-up papers exploring.
Okay, if there's no more questions, then I suggest that we head for lunch, which is in the cafe again, and we'll start again at 1:45.